In this PowerPoint, we're going to review how to balance a redox equation. It can be a little more complicated than the balancing that you've learned in the past because for redox equations, we must balance both mass and charge. All chemical equations must obey the law of conservation of matter. And the balancing process that you're familiar with is associated with this mass balance. We add coefficients to try to get the same number of atoms of each element on both the reactant and product side. For a redox reaction, though, where one substance loses electrons and another gains them, it's also important that all the electrons lost and gained are accounted for. In other words, the number of electrons lost by one substance in the reaction must equal the number of electrons gained by another. But the way that reactions are normally written, they don't show the actual number of electrons transferred. And you have to infer how many are involved through the change in oxidation state of the elements in the reaction. We're going to review a step-by-step process that will make it easier to balance both the electrons and their charge, as well as the mass of all the atoms involved. So first I'm going to show you the general steps, and then we'll apply them to several examples. So number 1, assign oxidation states to all the elements on both sides of the arrow to determine which element is being oxidized and which is being reduced in the reaction. Second, we'll separate the reaction into two half reactions. In one half reaction, we simply show the oxidation process with the number of electrons lost on the product side. In the other half reaction, we show the reduction with the number of electrons gained clearly written on the reactant side. We can now balance each half reaction separately. First, we do a mass balance, adding coefficients as necessary to make sure we have the same number of atoms of each element on either side of the arrow. Then we balance each half reaction with charge by adding coefficients to the electrons to make sure that the sum of the oxidation states on each side of the arrow equals each other. Once each individual half reaction is balanced with respect to mass and charge, we then make sure they balance each other by adjusting the coefficients so we have the same number of electrons transferred in each half reaction. Finally, we can add the two half reactions back together, making sure to cancel out the electrons and any other compounds or elements found in the same form on both sides of the arrow. And of course, the last step, we should always double check that the number of atoms and the total charges are equal to each other on each side of our final net equation. So these general steps do vary a little bit based on the type of redox reaction we're dealing with. If the redox reaction occurs in acidic or basic solution, which many redox reactions do, we can actually use charge on the hydrogen and hydroxide ions in those solutions to help us with the charge balancing overall. I'll show you an example of each of these types. Let's start with a simple redox equation. And the first step, again, is to assign oxidation states to each element and determine what's being oxidized and reduced. And we only have two elements here, copper and iron. Their oxidation states are simpler to figure out because we're dealing with just ions and neutral elements. So copper starts as a +2 ion on the reactant side and becomes the neutral metal on the product side. The oxidation state goes from +2 to 0. The charge is reduced, so copper is our element undergoing reduction. Iron, on the other hand, starts as the neutral element with an oxidation state of 0 and ends as the cation with a charge of +3 on the product side. The charge becomes more positive, so iron is the element being oxidized. The next step is to separate this reaction into smaller half reactions. And for the first half reaction, we'll take the element being oxidized, iron, and separate it out. We'll keep elemental iron as the reactant and the ion as the product. but we'll add electrons to the product side, showing that the neutral metal had to lose electrons to become the positively charged cation. And we use a lowercase e with a negative superscript to indicate the charge on the electrons. For the reduction half reaction, we'll show only the substance being reduced. And again, we keep the formulas of the reactants and products the same as the original equation. So the copper cation on the left and elemental copper on the right. We do add electrons to the reactant side this time because reduction involves the gain of electrons. Next, we'll balance each of these half reactions by mass. And all this means is adding coefficients if necessary to make sure we have the same number of atoms of each element on each side of the half reaction equations. So for the oxidation reaction, we have 1 iron on the reactant and 1 iron on the product side, already mass balanced as it is. It's the same situation for the copper in the reduction half reaction. We ignore the electrons during the mass balancing of the individual half reactions. We'll account for those next. And we'll do that by balancing each half reaction with respect to charge. And that simply means figuring out how many electrons must have been lost in the oxidation half reaction to account for that change in charge, and adding that number as a coefficient on the electrons on the product side. And we do something similar for the reduction half reaction. So let's look at how this works. For the oxidation half reaction, we know that we went from a charge of 0 to +3 on the product side. In order for this to happen, the iron atom had to lose 3 negatively charged electrons. So we add 3 as a coefficient on the electrons on the product side. And now if we add the total charges on the left and right sides of this half reaction, they should equal each other. So 3 electrons, each with a negative charge, is -3. If we add this to the +3 charge on the iron, also on the product side, it equals the total charge on the reactant side of the equation, which is 0. So the oxidation half reaction is now charge balanced. We'll do the same charge balance for the reduction half reaction. This time we go from +2 for copper to 0 on the products. The copper ion had to gain 2 electrons to do this, so we added 2 coefficient in front of the electrons on the reactant side. Now when we factor these 2 negatively charged electrons into our total charges for the half reaction, the left side of the arrow should equal the right. So +2 plus 2 -1 charges does equal 0. So now our reduction half reaction is charge balanced as well. Before we can add the 2 half reactions back together, though, we need to balance the electrons between the half reactions. And this means we need to make sure that the number of electrons in each half reaction is the same. In other words, all the electrons that are lost in oxidation have to be gained in the reduction process. So we have 3 electrons lost in oxidation and 2 gained in reduction. This is clearly not the same. Unfortunately, we can't just change the coefficient from 2 to 3 on the reduction half reaction to get them to be the same. If we did so, the reduction half reaction would no longer be charge balanced. Instead, we need to increase both reactions to the same number of electrons while keeping the charge balance the same. And to do this, we figure out the least common multiple between the number of electrons in each half reaction. Then we multiply all the substances in the individual half reactions by whatever is necessary to increase the electrons to that least common multiple. So in this case, the least common multiple between 2 and 3 is 6. This is the number of electrons that we're going to try to get in each half reaction. So to do this, to get 6 electrons in the oxidation half reaction, we need to multiply that entire half reaction by 2. And I'll rewrite this below with the new coefficients. The oxidation half reaction now becomes 2 solid iron atoms on the left and 2 iron ions with a +3 charge on the right, plus 6 electrons total. And by multiplying everything in this half reaction by 2, not just the electrons, we've maintained the mass and charge balance we established in the previous steps. For the reduction half reaction, we'll need to multiply everything by 3. So here's the new reduction half reaction. 3 copper 2+ ions plus 6 electrons results in 3 neutral copper atoms. Again, by multiplying everything in this half reaction by one number, we maintain the mass and charge balance. And please note that we can multiply each half reaction by different numbers, so 2 for oxidation and 3 for reduction, as long as we end up with the same number of electrons overall in each reaction. This is to ensure that when we add together the 2 half reactions in the next step, the electrons cancel out. So that's what we'll do next. And remember that when you add together reactions, we cancel out anything that occurs in the exact same form on opposite sides of the arrow. So we have 6 electrons on the product side and 6 electrons on the reactant side. These can be canceled out in our net process. It doesn't mean that those 6 electrons aren't lost or gained. It simply means that we don't see the electrons as reactants or products in the final net reaction. You can consider them as reaction intermediates. And if there were other substances in the same form on opposite sides of the arrow, we could also cancel them out. There are no other common substances for this reaction, so we just add everything else together. All the reactants together on one side of the arrow and all the products together on the other side. And this is our final balanced redox equation. As a final check, we should just make sure everything remains mass and charge balanced. So we have 2 iron on each side of the arrow and 3 coppers. That is still mass balanced. Now, for the charge balance, on the reactant side, we have a 0 charge on the 2 irons and 3 coppers, each with a +2 charge. On the product side, there are 2 irons, each with a +3 charge, and 3 coppers, each with a 0 charge. If we add together the charges on each side, we find that we get +6 and +6 on each side of the arrow. This is still charge balanced as well. Now we can say that this redox equation is fully balanced with respect to both mass and charge. Now let's look at a little more complicated example. And this time we're going to balance a redox reaction that occurs in an acidic solution. The first step is the same. Assign oxidation states and determine which element is oxidized and which is reduced. We have 3 elements this time, so we need to determine the oxidation state on each. We'll start with iron. It goes from a +2 charge on the reactant side to +3 on the product. The charge becomes more positive, and this is the opposite of reduction, so iron must be the element oxidized. The next element, manganese, is a little trickier to determine the oxidation state for. On the reactant side, it's combined with oxygen in a polyatomic ion, permanganate, with a -1 charge. We have to use our rules of hierarchy to assign one element first and then the other in this polyatomic. If we were to look at these rules, we'd see that the transition metal manganese, like manganese, aren't even mentioned in the rules. Nonmetals, like oxygen, are found in Rule 4. So oxygen takes precedence over manganese, and we assign its value by the rules as -2. There are 4 oxygens in the polyatomic formula, so we multiply the -2 charge by 4 to find that we have a total negative charge of 8 in the polyatomic. The net value, the sum of positive and negatives, has to equal the charge on the ion. So in this case, it has to equal -1. And this means that our positive charges have to be +7. And since we only have one manganese ion left, that manganese ion has to take on that full +7 charge. On the product side, manganese is present as a simple monoatomic ion, so the charge on the ion is the oxidation state on the element, +2. And this means that the charge on manganese decreases or is reduced from left to right. So manganese is the element that undergoes reduction. And it turns out that in this unbalanced redox reaction, oxygen is only present on the reactant side. As part of our balancing process, we are going to have to mass balance the oxygen. But since this reaction occurs in acidic solution, we can actually use the water it's dissolved in to help us with that mass balance. And I'll show you that variation in the general balancing procedure on the next slide. But first, we have to separate our unbalanced reactions into half reactions. So for the oxidation half reaction, we take the element oxidized iron, and we keep it as iron +2 on the reactant side and iron +3 on the product side. And we just add the electron symbol to the product side to show that electrons are lost during oxidation. For the reduction half reaction, we carry down the entire formula that contains the element being reduced. So permanganate ion on the reactant side and manganese with a +2 on the product side. So this is an important point in creating our half reactions. If the element oxidized or reduced is found in the original reaction as part of a compound or a polyatomic ion, we carry the full formula for that compound or polyatomic into our half reaction. This means that we may have elements present in the half reaction other than the ones being oxidized or reduced. Finally, note that we add electrons to the reactant side for our reduction half reaction to show that electrons are gained during reduction. So the next step is to balance each half reaction by mass. And we're going to add a few steps here to help us balance the oxygen. And we can do this because we're told that this reaction occurs in acidic solution. This is an important point. So first, we balance all the atoms except oxygen and hydrogen. And for the oxidation half reaction, this is straightforward. There's only iron present, and it's already present as 1 and 1 on each side, so it's mass balanced as it is. For the reduction half reaction, we balance manganese first. And it's also present as 1 and 1 on each side of the arrow. So manganese is mass balanced, but oxygen in the permanganate is not. So to balance our 4 oxygens, we're going to add water to the side that lacks oxygen. So this means I add water to the product side of this reduction half reaction, and I add 4 waters total so that I balance the 4 oxygen atoms on the reactant side. Of course, this also means, since I've added water, I have now introduced hydrogen into my equation. 8 hydrogen, to be exact. So I have to balance this element as well, and I do so by adding hydrogen ions to the side that lacks them. So this means that I add 8 hydrogen ions to the reactant side. And now my half reaction is mass balanced. So I can add water and hydrogen to balance everything because I was told again that this reaction occurs in acidic solution. That means that I know that both hydrogen ions and water are already present. With our mass balance done, we can now proceed to balancing the charge within each individual half reaction. We'll do this by adjusting the coefficient on the electrons so that the charges on each side of the arrow equal each other. So for the oxidation half reaction, we have +2 on the reactant side and +3 for the iron on the product side. And we also have a -1 for the electron. And it turns out that the sum of the charges on the product side already equals the charge on the reactant side with that one coefficient on the electron. So we don't have to change anything. For the reduction half reaction, I'm going to simplify the process by dealing with the net charge on the permanganate ion instead of the individual charges on manganese and oxygen. So the net charge for permanganate is -1. I'm going to skip over the electrons for right now and just deal with those 8 hydrogen ions. So each of them have a +1 charge. On the product side, I know that I have a +2, and my water molecules have a net charge of 0. So I'll simplify by just dealing with that net charge. Now, our total charge on the product side is actually +2. So in order for our reactant charge to equal +2, we have -1 and +8. We need 5 additional negative charges. And we get this by adjusting the number of electrons to 5. Now, if we add together -1 plus 5 times -1 plus 8 times +1, we get a total charge of +2. The charges on both sides are equal to each other, and we are now charge balanced for our individual half reactions. Our next step will be to balance the electrons between the half reactions. And again, this just means getting the same number of electrons in both half reactions. We have 1 electron in the oxidation half reaction and 5 in the reduction. The least common multiple of these two numbers is 5. So we simply need to multiply everything in the oxidation half reaction by 5 in order to get the same number. Now I'll rewrite both half reactions below with the adjusted coefficients before I proceed to the last step, which is to add everything together. Now, as I add these two reactions together, remember that I cancel out everything that occurs in the exact same form on each side. So I have 5 electrons. I know that I can cancel out in both oxidation and reduction. That's the only thing in common on both sides. So we add everything else together. And our final balanced redox equation is 5 iron with a 2+ charge plus 1 permanganate ion plus 8 hydrogen ions react to produce 5 iron ions with a 3+ charge, 1 manganese ion with a 2+ charge, and 4 water molecules. It's always a good idea to do one final check to make sure everything remained mass and charged balanced throughout. So we have 5 iron, 1 manganese, 4 oxygen, and 8 hydrogen on each side. The mass balance remains true. The charges are a little bit more complicated this time. We have a total of +10 for the iron, -1 for the permanganate, and +8 for the hydrogen ions. These have to equal everything on the product side. And we have +15 this time for the iron, +2 for the manganese, and water is neutral, so our total product charge then is equal to +17. On the reactant side, +10 minus 1 plus 18 also equals +17. The equation is also charge balanced. Now we'll look at one last example. And this time we're going to balance a redox equation in a basic solution. So this will add one more step to our balancing process. We start out the same way as all the other equations though. We assign oxidation states and determine the element oxidized and reduced. So in this case, the iodine on the reactant side has a -1 charge, and on the product side, it's the neutral. It's in a neutral element diatomic molecule. So the iodine charge actually increases from reactants to products from -1 to 0. This is oxidation. Next, we have a permanganate ion, and as we learned in the last example, oxygen is higher than manganese in our hierarchical rules for assigning oxidation state. So we give the oxygen its charge of -2, as outlined in those rules. We have 4 oxygens, so the total negative charge is -8. Since the ion as a whole has a net charge of -1, our 1 manganese ion must have a +7 oxidation state to give us that. And on the product side, manganese and oxygen are found in a neutral compound of manganese dioxide. Again, we assign oxygen first with a charge of -2, as outlined in the oxidation state rules. We have 2 oxygens in this formula, so this is a total negative charge of -4. And since this is a neutral compound overall, the manganese must have a +4 charge to balance those oxygens. So the charge on oxygen doesn't change from left to right. It's -2 throughout. But the charge on manganese does. And to go from +7 to +4, manganese must be reduced. Now we can separate our reaction into oxidation and reduction half reactions. And our oxidation half reaction will be the iodide ion on the left going to the neutral diatomic iodine molecule on the product side. And we'll also put in the electron symbol on the product side to show that electrons are lost during oxidation. For the reduction half reaction, we have our reactant permanganate ion plus an electron symbol to show that electrons are being gained during reduction. On the product side, we have manganese dioxide. The next step is to balance each half reaction by mass, and we're going to follow the same steps we did for the acidic solution. If we add water and hydrogen ion to balance the oxygen, however, we do need one additional step for basic solutions. We have to balance the hydrogen with hydroxide. So let's see how this works. First, we mass balance the elements other than oxygen and hydrogen. So it's iodine in the oxidation half reaction and manganese in the reduction one. So for iodine, we have 1 on the reactant side and 2 on the product, and we'll add a 2 coefficient to the iodide ion to get the same number on each side. Now for the reduction half reaction, we already have 1 manganese on each side of the arrow. So that element is mass balanced. We have to deal with the oxygen next. We do actually have oxygen on each side of the arrow this time, 4 on the reactant and 2 on the product. We're going to follow our redox rules for balancing oxygen and add enough water molecules on the side that needs it to get the same number throughout. So we need 2 more oxygens on the product side. We add 2 water molecules to the products. And of course, we added hydrogen with the water molecules, so we'll balance the hydrogen by placing hydrogen ions on the reactant side. And we'll need 4 to balance out the 4 hydrogens in the water molecules. Now, here is where we have to add a little more than in the previous examples. This reaction was done in basic solution. So any hydrogen ion present likely comes from the dissociation of a solvent water molecule. And we need to show this dissociation by adding in the other product, the hydroxide ion. And the easiest way to do this is to add hydroxide ions to balance the hydrogen ion. So for every hydrogen ion on the reactant side, we add the same number of hydroxides to the reactant side. In this case, 4. Now the hydroxide ion doesn't actually take part in the reduction process, so it'll also be present in the same amount on the product side. We add the same number to products, and this allows us to mass balance our hydroxide ion. Now, the reduction half reaction is mass balanced. We have one last step. We can simplify this reduction half reaction just a little bit. On the reactant side, where we have both hydrogen and hydroxide, we can actually replace these with the water molecules that these ions originally came from. I'll show that replacement when I write these half reactions on the next slide. So here are the two half reactions again. And notice that I've replaced the 4 hydrogen ions and 4 hydroxide ions on the reactant side of the reduction half reaction with 4 water molecules. And we now have water on both sides of our reduction half reaction. We'll cancel those out in our last step when we add everything back together. Before that, though, we need to charge balance each individual half reaction and then balance the electrons between the two reactions. So let's start with the charge balance for the oxidation half reaction. So we have 2 -1 ions on the reactant side. On the product side, we have a neutral iodine molecule. And to raise the charge to the same value as the reactant side, we just need to adjust our number of negatively charged electrons to 2. So we add a 2 coefficient in front of the electrons. And now 0 plus 2 times -1 gives us -2 on both sides of the oxidation half reaction. Now for the reduction half reaction, the water molecules are neutral overall, so we have 4 times 0. We'll simplify the charges on permanganate at this stage by just taking the total charge on the polyatomic, which is -1. I'm going to leave the electrons till the very end, since this is the only thing I can adjust in order to do the charge balance. We'll move over to the product charges. And since manganese dioxide and water are both neutral molecules, we'll assign each a total charge of 0. Our only charge on the product side comes from the hydroxide ions then, and we have 4 of them, each with a -1 charge. As a result, our total charges on the product side is -4. On the reactant side, we have 0 plus -1. We need 3 more negative charges to balance out. And so we do that by adding a 3 coefficient to our electrons. Now, each half reaction is mass and charge balanced. We need to balance the electrons between the 2 half reactions before we add them together. So we have 2 electrons lost in the oxidation half reaction and 3 electrons gained in the reduction one. The least common multiple between these two is 6. So that's what we'll try to get in both half reactions. That means we're going to multiply the oxidation half reaction by 3, and we multiply everything in that reaction. And it gives us 6 iodide ions on the left and 3 iodine molecules and 6 electrons on the right. For the reduction half reaction, we'll multiply everything by 2. It gives us 8 water molecules, 2 permanganates, and 6 electrons on the reactant side. On the product side, we have 2 manganese dioxides, 4 water molecules, and 8 hydroxide ions. And finally, we can add together the 2 half reactions and cancel out anything that is in common on both sides. So first we'll cancel out the 6 electrons from both half reactions. But we also have water on both the reactant and product side. It doesn't completely cancel itself out because we have 8 on the reactant side for the reduction half reaction and 4 on the product side. However, the 4 water molecules on the product side will cancel out with 4 of the 8 on the reactant side. And so that will leave us with a net of 4 water molecules left on the reactant side. And now we can add everything that's left. And we end up with 6 iodide ions plus 4 water molecules plus 2 permanganate ions on the reactants, and 3 diatomic iodide molecules plus 2 manganese dioxide and 8 hydroxide ions on the products. And of course, it's a good idea to double check that everything is still mass and charge balanced throughout. So we have 6 iodines on the left and 3 times 2 equals 6 on the right. We have 4 times 2 equals 8 hydrogens on the left and 8 hydrogens in the hydroxide ions on the right. We have 4 oxygens in the water plus 2 times 4, which gives us 8 oxygens in permanganate. So that's 12 oxygens total on the right. And we also have 2 times 2, or 4 oxygen and manganese dioxide, plus 8 in the hydroxides. So 4 plus 8 gives us 12 as well on the right. And finally, we have 2 manganese on the left and 2 manganese on the right. Everything is still mass balanced. Now for charge, we'll just look at total charge on each ion and molecule. We have a -6 for the iodide. Water is neutral. And then we have a total of -2 for the 2 permanganates. That gives us a net charge of -8 on the reactant side. On the product side, our first 2 molecules are neutral. But we have the -8 charge with our hydroxide ions. So this reaction is still charge balanced as well. In summary, oxidation-reduction reactions must balance for both mass and charge. And to do this, we separate and balance individual half reactions and then add them back together. The water, hydrogen ions, and hydroxide ions in acidic and basic solutions can also be added to the reaction to complete the mass and charge balance.